Well, good morning, everyone. I'm Ryan Fox on the Developer Relations team here at Algorand, and I am thrilled to welcome both Jay McCarthy and Christopher Swenner from Reach. They are the co-founders there, and they're going to give us an introduction to building Dapps with the Reach language, tell you all about what their tools can do, how easy it can be to build Dapps, and also how safe it is. The point of the Reach language is really to abstract away all of the underlying blockchain stuff and just think about the business logic up here on top. It's a really great way to look at developing blockchain programs in a higher level. Don't have to worry so much about how to actually think about writing teal. And also they abstract it down to other blockchain languages as well. But I know they're going to focus on Algorand today. We're thrilled to have you guys both here at the Algorand Developer Office Hours. And with that, I'm going to pass it over to Jay. Good morning.
Hey, how's it going, everyone? Nice to see you all. My plan for today is to give you a bit of a tour of how to use Reach, and not so much have like a workshop where I teach you every little detail, but I just want to kind of show you what like a detailed Reach program looks like to get you excited about what you could build. So to start off with, I think that Ryan did a good introduction to what Reach is. Reach is a domain-specific language that's designed for building decentralized applications. And our main goal is to broaden who can write Dapps. Right now, it's really difficult to learn the underlying technologies that are used in most consensus networks. So if you're familiar with Algorand, when you write a Dapp in Algorand, you've got to write a teal program, which is essentially writing a program in assembly. And this makes it so it's extremely performant Algorand contracts, but it's it's a very high barrier to entry. And even in other consensus platforms, that have high-level programming languages, oftentimes you have to think at a very different level of abstraction than the business logic that you're really interested in. And so the goal of Reach is to make it so that you don't have to worry about those details, and also that you can have more assurance that the code you're writing is correct. Now, if you want to learn about Reach, then the best thing to do is to go to docs.reach.sh. So that's docs.reach.sh. And so this is our documentation, and the page will look like this. I highly recommend that you check out our overview, which is a very short read that gives you an idea about what Reach does. And if that's interesting to you, and of course, what you see today is interesting to you, then the tutorial has basically like a 10-step process for building your first Dapp. In this Dapp, what you do is you basically build a way for two people to wager over the outcome of a game of rock, paper, scissors. Now, what I'm going to do today, however, is not something that is fully explained on the documentation. What I want to do is walk you through a Reach program where you have a wager over a game of tic-tac-toe. Now, you may say, well, why is there a rock, paper, scissors, and tic-tac-toe? What are these dumb games? The thing is that these dumb games are things that people kind of intuitively understand. Like, I can go downstairs to my kids playing at recess and ask them to explain to me rock, paper, scissors, and tic-tac-toe, and they'll be able to explain it. So by presenting Reach through these common games that most people understand, makes it so we can focus less on the domain that we're studying, i.e. like the actual rules of the game, and we can focus instead on the ideas of Reach programs. Now, over here in this window, I have my Reach program. And I'm not going to explain every single line from top to bottom. I'm going to kind of jump around a little bit. So bear with me a little bit. So in this Reach program, the syntax of Reach is almost identical to JavaScript. So what we're seeing right here is some basic stuff where we're defining the rules of tic-tac-toe. And I'll come back and look at this in a moment. Now, as I scroll down, what I get to is I get the logic of my application. And my Reach application is going to have two different people that are going to play it, that we're going to call Alice and Bob. Now, most of the time when you think about a Dapp, until you have been infected with the reach mindset, you might think about the main thing that you need to worry about with a Dapp is what is the state that exists on the blockchain, and then what are the valid state transitions that are possible for that object that is out there. And we think that this is a confusing way to think about things, because what is often more important for an application is what the individual actors in the program do. So what reach does is what you're going to do is you're going to specify the behavior of each participant in the program. So in this case, where there's going to be two players, Alice and Bob, who are going to play tic-tac-toe. But if you think about another kind of interaction, like let's think about a loan, there's the person giving the loan and the person receiving the loan. You're going to focus on what they do. Or let's think about something else where you're going to have an auction. So you're going to have the person proposing the auction, all the bidders, and then you're going to have the winner. So there's kind of three roles. And of course, that winner is kind of the same, is kind of one of the bidders. So anyways, so when you think about a reach application, you want to think about who is the actor that's actually doing something. Now, what we do is we're going to specify basically an interface between each one of those participants and an end user interface. And so that's what these little objects right here. And like I said, I'm just going to give you a brief overview and then we'll go through the details in a moment. So this right here is specifying the behavior that each one of these actors can have with, think of it like their command line interface or their web interface or whatever. Now, inside of this block of code, we're going to actually specify what happens as we run this program. The first thing that we do is we do stuff that only Alice does. So here we say a.only. So this means that Alice only does this. And then we see here a.publish. Now, one of the concepts of reach is that there is this, you have these participants and they can publish information out to the entire world. Now, this is not like a normal programming language where you think about, okay, well, I have this program and it opens up a socket to that program and it sends a message to that one. Because of course, on the blockchain, when you publish information, you're publishing it for everyone. And so this is the concept that's built into reach. So in this program, what's going to happen is that Alice is going to publish how much she wants to wager on this particular game of tic-tac-toe. And then what Bob is going to do is he is going to agree to that, and he is going to pay that amount, just like she's going to pay that amount. Then what's going to happen is that the players are going to enter this while loop right here. And the idea of this while loop is they're going to continue playing until the game of tic-tac-toe is done. And when it's A's turn, A is going to get a move and publish it. And when it's B's turn, B is going to get a move and publish it. And then eventually the game will be over, and we'll be able to figure out who the winner is. If the winner was Alice, then she'll get more money. And if the winner is Bob, then he'll get more money. But if there was a tie, then they'll both split the money and they'll get their wagers back. Now, you may be thinking, this is a dumb game because we know that you can always tie a game of tic-tac-toe. So that's why, don't spend too much mental energy stressing about whether you really want to launch this program. Okay, so I'm now giving you kind of a brief overview of the way that a reach program works. You specify the rules of whatever you're doing, and when you write this part of it, you're basically just writing a JavaScript program. Then what you do is you specify how the individual participants interact with their user interface. Then what you do is you specify the different steps of the program. Now, what do you do now? What do you do after that? Well, the next thing you do in a reach program is you're going to write the actual JavaScript front ends that will be the behavior of this program. So here, for example, what we're doing is we're going to initialize Alice and Bob with test accounts. We're going to deploy the contract and attach to the contract. And then what's going to happen is that we're going to go off and we're going to create a promise for running A and a promise for running B, and then they're going to run. And then this code right here is the code that interacts with the actual front ends. So when the reach program says, I want to go figure out what the wager should be, or I want to go figure out what move I should make, what that's doing is it's going to call this function over here in the JavaScript code. And so this right here is a completely normal JavaScript program. It's just a short 67-line JavaScript program that really treats the blockchain as being non-existent. In fact, nowhere in this do we write down any details about the fact that we're writing a blockchain program, and we're not writing a program where Alice and Bob just like directly communicate with one another. This right here is just a completely vanilla JavaScript program where all of the interaction with the blockchain is abstracted away behind the reach standard libraries. When we actually run this, what's it going to look like? So I'm going to show you what it's going to look like, and then we'll finally be ready to look at every single detail. So I previously ran this. We'll run it again in a moment. So when you run the program, what's going to happen is it's going to make a Docker image that's special for your program and start up a completely fresh Algorand instance. And the reason we're doing this is to test it really, really quickly, because it's kind of a burdensome, right, to publish it on the main net, actually commit algos to it. You have to decide whether you want the test net or the beta net or whatever. So anyway, so what's happening here is that we're just going to start up a test instance. So then what's going to happen is that we're going to see all these printouts, and these printouts are like, Alice has published the parameters of the game. And why is it happening? Well, that's happening because our program right here said console log name publish parameters of the game. And it says Bob accepts the wagers. That's right here in the accept wager function. And then we're going to see these things that say Bob chooses a move. Okay, so that's what this says. It says so-and-so chooses a move, and then we print out what the state looks like. And then we choose the move. And so right here, I've played it so that they play a random game. So Bob chooses a move, and then Alice chooses a move, and they're just randomly fiddling around, making really bad moves at tic-tac-toe because they're just randomly. And at the very end, they'll see the final state of the game. So it says ends with, and then they see the final state. So this is what it looks like to run this program. Now, behind the scenes, what actually happened is that the Reach compiler generated a teal program. And I'd like to give you a glimpse at that teal program. Now, if you've used teal before, I hope that you'll be frightened by this experience. And if you haven't used teal before, well, I hope you'll be even more frightened by this experience. So we want to go look at this. So let's look at the teal program that is for the main step of the program. So I believe that it is, I think it's this one. So this right here is the teal program that gets generated for when we submit the move. So if you thought about teal before, one of the main things that you do is you're approving transactions that are submitted. So what this does is it goes and it makes sure that there's an application transaction and make sure that, amounts match fees and receivers match senders. It's sort of checking all these invariants. And these are sorts of things that you might think about doing yourself. And then what it does is it then transitions to actually running your Reach program on inside of teal. One of the things that Reach does is it guarantees that your state on the blockchain is never more than 256 bits. And it does this for efficiency because you pay for every cell. Well, when I say pay, you have to have a minimum balance of that amount. And so it's like you're paying because you're setting aside the money. Okay, anyways. So what we're doing right here is we're verifying that we're in the correct state. And then what we're going to go do is we're going to analyze the arguments that we've been given to check to make sure that this move that was been submitted is a valid move. So all this is logic for how to do that. Right here, we're looking at a big giant byte string that represents the state of our game, and we're doing all sorts of tests to make sure that this move is one that's allowed, that it's not one that we're not allowed to look at. And then we're updating the state so that we can store it, and we're checking to see if there's a winner. And if there wasn't a winner, then what we're going to do is we're going to do one thing, but if there was a winner, then we're going to do something else. You're not meant to understand this program, and you're meant to look at this program. When I say you, I mean you, the audience. You're supposed to look at this and you're supposed to say, how in the heck would I ever write this myself? And that's really the sense that we would like you to feel every time you look at the teal program that's generated by a Reach program. So this right here is a 432-line teal program. And if you're familiar with the details of teal, every teal program is limited to 1,000 bytes, including its arguments. And so because of that, we actually have, this program is quite large because there are many different steps. And each one of those is actually a totally separate teal program. So in fact, we didn't generate 432 lines of teal. We really generated more like 2,000 or 3,000 lines of teal for this short application. And the reason that we have so many is to make sure that each step does its own things. So now that you've sort of seen the swath of where we're going to go. Now let's dig in to the details. So like I said, when you write a reach program, you're writing a JavaScript program. So right here is a very simple JavaScript implementation of tic-tac-toe. So we say that there's going to be 3 rows and 3 columns, and we're going to store our board as 9 booleans, as an array of 9 booleans. And then we're going to store the state of our game as whether it's X's turn, which is going to be a bool, and then we're going to have 2 boards, the board of where X has put their pip and the board where O has put their pip. Now you may think, why are we storing 2 different boards? This is kind of like we're being elite hacksaws, because we want to make it so that rather than storing like a number on each spot, we want to store 2 different things, because of course there are 3 states. There's not 2 states, because you can have empty, 0, or X. And so we're kind of getting around that. We don't want to just store a number on each one, because then the state would be too big. Okay. Then what we'll do is we'll represent an empty board as just an array of 9 falses. Then we'll say that the initial state is based on whether or not X is first. And so we'll say if X is first, and then the 2 boards will be empty. We're going to write a little helper function that's going to look at whether or not a cell is occupied. So we'll write this function called cellBoth that's going to take a state and then an index, and we're going to say we want to look at the X's in that spot and the O's in that spot. Okay. Now what we'll do is we'll write another function that's called marksAll, which is going to give us the board that's going to tell us whether or not all the cells are occupied. So we'll call cellsBoth on each little thing, and now we'll get the entire board. We'll write this little helper function to tell us to turn a row and a column into a cell. So we'll do C plus R times calls. Then what we'll do is we're going to make this little helper to check a sequence. We'll have the row that we're going to start at, the column that we're going to start at, and then the difference in row and the difference in column. So we'll look at the board, cell RC, dr CDC, R dr dr, R CDC. This is just a way of looking at 3 things. Now, why are we doing this? Because we're going to write a function called row that's going to look at the sequence starting at this row, and we'll go 1 ahead, and then the column starting at this column, then go 1 down. So the idea here is that we're looking to the right, we're looking down, and then how do you know if you're winning? Well, you first check row 0, row 1, row 2, column 1, column 0, column 1, column 2, and then the diagonals. So this is one diagonal, and this is the other diagonal. We then have another check to make sure that the board is complete. And this we check to make sure that every cell is occupied. And now we can finally, once we've sort of coded up all this stuff to look at the state, we can now write our actual game logic. So the game is done when X wins, or O wins, or the whole board is complete. So that's how we know when we're done. A legal move is one that is for a valid cell. And a valid move is one where it's not occupied by either of the players. Okay. So now we'll write our first function. It's called getValidMove. And so what this is going to do, it's going to interact with the front end and call the getMove function. It's going to assume that it got a legal move and assume that it got a valid move. This assume right here is kind of like a runtime check. It's going to check to make sure that the front end, which we don't trust, actually submits us a legal move and a valid move. And if it doesn't do that, if it gives something bad, then we're gonna throw an error. It's also integrated into the theorem prover that is included inside of Reach, which I'll comment on later. Then what we're going to do is we're going to run another function that's called applyMove, and this one is going to actually run the effects of whatever the move is. So we're going to require that the move is legal and require that it be valid. And this is also like a runtime check. But this runtime check is double checking a front end to make sure that the front end did the right thing. And this runtime check is double checking that like a anonymous client on the internet that sent us a message did the right thing. Now, you may think to yourself, like, how worried should I be about this stuff? If you forgot to write this, Reach will complain. If you forgot to write this, Reach will complain. If you forget to write both of them, Reach will complain. So Reach guarantees that your program behaves the rules and includes all the proper runtime checks. So then how do we actually apply the move? What we do is we say, well, first, whose turn is it? And we flip whose turn is it. And if it's X's turn, then we set the cell true in X. And if it's O's turn, then we set the cell to true in O. Now we can write these little functions as called the winner is X versus the winner is O. And this just calls the winning predicate on X or the winning predicate on O. Now, maybe you look at this code and you say, this isn't how I would implement tic-tac-toe, but hopefully you see that this is a totally reasonable way to implement tic-tac-toe. Maybe I use more arrows than you're used to using when you write your JavaScript programs, but hopefully it sort of makes sense as far as JavaScript programs go. And so that was, tic-tac-toe and 76 lines. Okay, but now let's look at the actual part of the program that does interactions with the blockchain. So here we'll go down to the actual program. So as I mentioned, what we're going to do is we're going to specify how each player interacts with its front end, and then what they do. And I thought that what we would do is we'd look at these in sequence. So we're going to see what the participants do, and then we'll go back to the interface from there. So the first thing that Alice does is she's going to call interact get wager. And so this is going to call this function right here, which is going to return a number. And actually, let's open up the JavaScript front end on the side so we can actually see the implementation of this function. So if you write here get wager, it says so-and-so publishes the parameters of the game, wager is wager amount, and then it returns it. So this function right here, the existence of it is specified right here, and we call it right here. Now the next thing that we're going to do is, there's kind of an advantage to going first in many games. And so what's going to happen is that Alice and Bob are going to have a coin flip determine who goes first. And the way that we're going to do that coin flip is that Alice is just going to generate a random number. So we call interact.random. Now, you may think to yourself, like, why doesn't Reach just support randomness? Well, Reach programs are entirely deterministic in their structure and in their values, except for the fact that there are these front-end functions. And so all non-determinism is hidden in those front-end functions. And so randomness is really common. So we have a standard library that's called hasRandom to say that your interface is your front end is going to provide a randomness. And we have a standard library implementation of that uses cryptographically secure randomness functions for you. Okay, so we're going to get a random number. But now, if we just publish this random number, then Bob could look at the random number and then choose the appropriate other random number to make himself win. So what we're really going to do is we're going to do a digest of this, which is like a cryptographic commitment. Now we're going to publish that wager amount and the commitment, and we're going to pay the wager amount. In this pay right here, it goes into an escrow account controlled by our smart contract. Now, the only thing that I didn't comment on in this little block right here are these declassifies. So one of the things that Reach does is it uses a security information flow system to guarantee that values that come from front ends are protected in their privacy. So once the front end sends something to the back end, it's protected until it is explicitly declassified. This is sort of like saying, double clicking, yes, I really do want to share this. And so we have to declassify the wager right here before we publish it. Similarly, the randomness came from the front end, so therefore its digest is also private, so therefore we have to declassify that if we want to share it. All right, now let's look at what B does. So what B does is he calls accept wager. And so accept wager is over here, so it just prints out a message and returns. And then what he does is he gets a random number, declassifies it, and immediately publishes it. Now notice that he doesn't commit it because Alice has already committed to whatever her coin flip result is going to be. So there's no way that she can manipulate that. So what we do is we publish his coin flip and we pay his wager amount. Now what happens is we go back, and what Alice does is she declassifies her coin flip and then publishes it. And now this publish is now in the context of the consensus code. And so here we require that the commitment that she published earlier match a digest of what she just published. And so this right here is a guarantee to keep her honest. Now you may say, well, what would happen if I forgot this line? If we forgot this line, then what we're going to do is we're going to have an error that's going to say, well, it's going to check and make sure that this commit A actually always gets read. And so since it's not otherwise read, it would be an error. Okay, so now what we'll do is we'll figure out who's first. And so we have these two random numbers, so we've got to interpret them as a coin flip. So the easiest way to do that is to just look at the parity of each one. So we take A's coin flip and we'll see if it's odd or even, and then B's coin flip and see if it's odd or even, add those together and see if that's odd or even. And if it's even, then we'll have X go first, which is Alice. So what we'll do is we'll set up the initial state of our program, which is the tic-tac-toe initial state where X is first. Then what we're going to do is we're going to have invariant that the balance over time is always 2 times the wager. So one of the things that you do when you're writing a reach program is you're simultaneously verifying it. And here what we need to do is we need to explicitly write down what is true before and after each iteration of the loop. And in this case, it's that the wager, the balance of the escrow account stays a constant number. And then we're going to have a while loop. While the tic-tac-toe is not done, we'll say, is it X's turn? If it's X's turn, we'll finish the last transaction, have A get a valid move, and this get valid move function is this function. Now, for testing purposes, I made it so it just randomly picks something, but you could make a user interface where someone clicks, etc. They get their valid move, they publish that valid move, and then we update the state by applying the move and then continue. And if it wasn't X's turn, well, then it would be B's turn. And if it's B's turn, then we will have B get the valid move and publish, and then move on from there. So then when we're done with the while loop, that means that the tic-tac-toe state is done. So now what we can do is we can say, well, was X the winner? And remember, X is Alice. And what we'll do is we'll return the number 2A as 2 and 2B as 0. Otherwise, 2B will be 2 and 2A will be 0. Otherwise, and after that, if it's a draw, then they'll both be 1. And we'll transfer 2A times the wager amount to A and 2B times the wager amount to B. And then we'll commit and we'll finish. So every time you do a publish, it sort of like transitions into the consensus code. We call these things modes. Let me just show you a little picture. So your program starts and it's in what we call a step state. And in a step state, you can run an only thing, and then only you can do interactions. And then you can do a publish or a pay and move to a consensus step, where you can do things like whiles, transfers, and so on. And then you can move back into step when you call commit. And then at the very end, what we're going to do is we're going to have each Alice and Bob print out a little message that says this is how the program ends. So altogether, this program is 150 lines of reach program, where half of that is just the idea of tic-tac-toe. So, 76 lines is what it means to be tic-tac-toe. And then the other 75 lines is how to deal with the interaction. And then our JavaScript program is just 67 lines of just normal JavaScript. Lest you think that this, thing that I showed you before was made up, let me just, run the program so you can see it running. Actually, by default, when you run things on Reach, it first runs it on Ethereum and then it runs it on Algorand, because when you write a Reach program, you're simultaneously writing something that works on multiple consensus networks, not just on one. And so here we're just going to watch in a game of Ethereum flip by, and it works the same way as I mentioned before. It starts up a little local Ethereum instance. And then now we're going to watch the Algorand one. Algorand Inc. is working on a DevNet where you can have it so that transactions will be processed as soon as they're submitted. But right now I don't have that new Algorand Inc. feature enabled. So this is going to run at network rate. So that means that every transaction is going to take about 5 seconds. In contrast, if I ran the Ethereum one at network rate, each transaction would take a couple minutes. So the Ethereum one just looks fast because it's the dev node, whereas this Algorand one is running at the actual rate it would run in the real world. So Alice is publishing the parameters of her game, and then Bob is going to do his, and then we'll just kind of see the same interaction that we saw before. There you see kind of like the main value that Reach is providing. It allows you to write your program in business logic that you would if you knew nothing about blockchain. It then allows you to write down the rules of your blockchain program at a very high level of specification. So you don't think about things like, do I use a stateful TL contract here, or do I use a stateless one? How exactly do I format the transactions? Do I do one transaction to the escrow and then another transaction to the contract. You don't have to worry about those details. Reach takes care of them for you all automatically. Behind the scenes in every single one of these interactions, like this whole program, as I mentioned before, it's basically like five steps, because it's this publish, that's one step, this publish, that's two, this publish, that's three, so this is step 3. Then it's this publish, which is 4, and this publish right here that is 5. So this program has 5 steps in it. And so there's those 5 steps, plus there's the initialization of it, so you got 6. So that means that there's going to be 6 contracts in this program. In addition to that, there's going to be 1 to handle the escrow account and 1 to handle the stateful application. So this whole program in total, and plus the stateful application is going to have what's called the clear state program. So this program really generates 9 different teal contracts. And of those 9 different teal contracts, 2 of them are stateful. 1 of them is for an escrow account, and then 6 of them are also stateless contracts that are for individual escrow accounts that handle each one of the different steps. And you could run this program many, many, many times once you have all those generated. And that complexity is something that you as a Algorand programmer don't need to worry about. Okay, so it's just about to end, because I think that if X runs next, then they're going to win. And if O goes, O chooses there, so X is going to win. So isn't that cool? So she's going to win, and then it'll be done. Okay, so Bob sees the final state, and there we go. All right. Now, when we were writing this program, there were a few things that we did to make sure that this, quote, theorem prover was satisfied. Now, what exactly is that? What's it doing for us? So I'm going to go into our program, and we're going to deliberately put in a mistake. So here's the mistake that we're going to do. We're going to accidentally make it so that when Alice is the winner, she doesn't get the entire wager back. So what I did is I changed this 2 right here to a 1. Okay, now why is this an error? The reason this is an error is that our reach program is responsible for a balance. And the thing is that since it's responsible for it, when our program ends, there's going to be no way to approve any more transactions to get those resources out. So if you are following the blockchain crypto world, you may have heard that occasionally people release contracts, and then something happens where the money that that contract is responsible for is locked away forever, and there's no way to get the money out. So that essentially means that the program has ended, but there's still a balance left over. And what reach does is it actually guarantees that this never happens. So I'm going to write reach compile right here. And what it's going to do is it's going to go and it's going to check every single path through the program, and it's going to make sure that those paths all end with a 0 balance. And you see right here that it tried to check 799 theorems, but 4 of them were false. These ones are duplicates of an earlier one, so we're just going to scroll up to the one that's unique. And so what it says is that there's a big message. So it says right here that it was trying to prove a theorem on line 93. So on line 93, so it's a theorem related to the application. And it's trying to prove the theorem 831. And 831 is the theorem that a certain value is 0. And that value is the balance. This right here is the balance. The balance has to be 0. And it's going to say that this could be violated if getWager returned 3, if the balance was 6, and if the way that the program ended was as described by this variable. So it's this. We could go look at the details, but basically K11 and K10, if we go look through this whole thing, it doesn't know that this is a tic-tac-toe program, so it can't show you a picture. But basically, if we were to go through and study what these values are, they're going to say Alice is the winner. So notice that it doesn't say if you chose this branch, then you could choose this and that's bad, because it doesn't know that you wrote some program called tic-tac-toe winner is. When it analyzes your program, it literally analyzes every single variable in your program, says what are the values that they could possibly be, including these giant 3x3 arrays of booleans. If you were sort of like a basic programmer, you may think to yourself okay, so there's 9, there's 2 of them, so that means 18, so it's going to look at all 2 to the 18 different ways of having all of those arrays, plus it's going to reason about all of the different combinations of the wagers, which is going to be 2 to the 64. So is it really going to analyze, 4.8 times 10 to the 24 different possibilities? And the answer is yeah, it does. It does analyze all those. And notice that it happens basically instantaneously. And the reason the way it can analyze all those is because it basically analyzes them all symbolically. Now, what if we had kind of the opposite problem? What if rather than leaving money on the table, instead, what if we tried to pay too much money? What if we tried to give Bob his money back when Alice died and give Alice all the proceeds? If we try to compile this program, we're going to get a different error. And this other error is going to printed it out really fast. And all of these things right here are basically saying that Alice won. And what it's going to say is that theorem, 820 could fail. And what 820 is that 817 is less than 819. So why is it a less than? It's checking to make sure that how much you're actually spending is less than or equal to what you actually have. So it's checking that. And so it's verifying that, okay, no, you're not allowed to do that. So you can't overspend, nor can you overspend. Now, notice that this program had, 799 theorems. So where did all those other theorems come from? Well, many of these theorems are automatically generated by Reach itself. So these ones related to the balance, that's automatically generated. But there are other theorems that are implicit in the way that you wrote your program. So for instance, notice that right here we wrote this require that Alice's commitment actually match her digest. Well, what if we go back here and we change this program? So let's make it so that rather than her declassifying her coin flip, what we'll do is we'll just say that her coin flip is going to be, well, we want her to go first. So that means that we're going to take whether or not B is odd, is even, that is. So we're going to look at whether it's even. And if it's even, then we would like it to remain even, so we'll give 0. Otherwise, it's going to be odd. And so what this is going to do is it's going to make it so that Alice always gets to go first. She's going to look at Bob's coin flip, and then based on what it says, just return what she wants. Okay. Now, when we run this program, it's going to have an error. And it's going to say that the theorem on line 118, which right here, see 118, this theorem right here could fail because the commitment for A doesn't match the coin flip for A. And so what Reach is doing is it's double checking that all the different steps of our program are all valid. Let's look at another one. What's another kind of theorem that's being checked behind the scenes? So notice that we have all these array accesses. Now, again, you may know that in other programming contexts, sometimes you accidentally write an array access that goes outside of bounds. And so if you do that, then you'll, of course, access, uninitialized memory or memory that shouldn't be what it's for. So that's what this legal move check is verifying for. So I'll get rid of this require right here. And when I get rid of that require, we're going to get a lot of errors. So all of these errors, what these errors are doing is they're checking the array bounds check. So it says on line 24, this array reference right here is not protected. And the reason it's not protected is because inside of this context, so inside of the code, the call at line 140, so inside of the apply move function, we haven't checked to make sure that it's actually a valid array reference. And that's what this require right here is doing. And what if we remove this assume? So if we remove that assume, then what's going to happen is that it's going to say that this require is not guaranteed to always return true on valid players of the game. So what Reach is doing when you write your program is it's not only giving you this high-level business logic where you get to write a JavaScript program like you would on any day of the week. It's not just making it so that you get to think about the logic of interaction between your participants. It's not just abstracting the details, the complicated details of Algorand. It's not just making it so that you can work on Algorand and Ethereum. It's also making sure that your program is correct against a whole category of errors that are common in all programs. It will verify properties that are unique to your particular program. And this is just a tiny taste of what Reach can do. If you're interested in this, go check out the documentation. And the documentation starts off with this overview, which gives you a brief perspective on what all the different features of Reach are. It even shows how to build web applications. Then what the tutorial does is it goes through a simpler game than the one that we just did of tic-tac-toe, and it focuses on rock, paper, scissors, and walks you through all the different features of Reach and how they're used in a program like this, including, of course, showing a way to deploy on the web. And this deploying on the web works on Ethereum and on Algorand. And then after you do the tutorial, if you want to go into deeper things, we have what's called the guide, which gives you a lot of the kind of the why and what about how Reach works. We have the workshop, which the idea of the workshop is, now that you've written a basic program and you have learned Reach, what series of programs should you write to really understand how decentralized applications are built? And if you go through this process, you'll become a blockchain expert. And finally, we have the reference, which is an extremely exhaustive technical reference on all of the different things that are possible inside of Reach programs. Reach is not a tiny fly-by-night operation where we don't have dedicated tools and support for new developers. We have an extensive manual. We have IDEs. We have support for VS Code, a VS Code extension that will help you use all the different features. When you install Reach, what you're doing is you're installing a Docker image, so you don't have to worry about setting up things, especially to match our environment. We support Windows. Basically, we support everything that you would like to do. And our goal is to make it so that the small number of blockchain developers will be completely dwarfed by the 20 million developers out there who are full stack developers who can now come into the blockchain space and start developing their interesting applications and hopefully deploying them on Algorand, which, as we know, is the fastest and most scalable network out there right now. This is kind of the end of my presentation, and I'm happy to answer any questions that you have or really talk about anything else that you'd like.
Yeah, great job on that. There was one question in the queue about debugging. I was wondering if you can talk about debugger options. I know we had mentioned in the answer VS Code extension.
So there's sort of two ways to think about debugging. There's how do I debug my JavaScript program? And so you write your JavaScript program, you can use all existing JavaScript tools for debugging, because this JavaScript program that really drives your program is completely normal JavaScript that will interact with all other existing JavaScript tools. When you, for instance, deploy on the web with React, the React debugging tools work nicely. Okay, now, what about when you want to debug your Reach program? Well, your Reach program really is this JavaScript program. So the only reason that there would be an error that would be unique to your Reach program would be like if there's a flaw in the Reach compiler. You know what I mean? And so basically, like, I have debugging tools as the author of the Reach compiler, but there's no special debugging tools for that. Basically, any problem in your program would show up as either a problem in your implementation of your front-end functions or in an assertion failing inside of your Reach program. So for instance, one of these requires or one of these assumes failing. And you don't see this, but like every single one of these assumes, I'm gonna go behind the covers a little bit. So your JavaScript frontend interacts with what we call the backend. It's called right here, build.index.main.js. So let me just open up that file real fast. So if we look at something like this right here in the get valid moves, to see how we have this assume, and this assume is on line 63. So what I'm going to do is I'm going to search for line 63 right here. Okay, so this assertion inside of our code, that corresponds to this line right here. And if this compiled JavaScript errors, it doesn't just error and say something broke deep inside of Reach somewhere. It actually knows what line of your program, including the call stack, at that line. So if this assumption fails, it is not going to say there's some weird error hidden in the bowels of the implementation of this thing. It's going to say that the assertion on line 63 of your program that was called from line 126, has the following error, and here are the values that I got, and here are the values that it's supposed to be. So anyways, the whole point of this is to say that we have designed reach so that existing development tools just automatically work with reach programs, because you're really actually writing a JavaScript program, and the normal JavaScript development tools continue working. And I don't know about you, but I've heard that JavaScript is a very popular language with many powerful debugging tools. Now, in addition to that, you can also use normal development practices when you're writing reach programs. So here's a little example of what I'm talking about. So one of the things that you might like to do when you're normally programming is to do unit tests. Well, let's write a little unit test for whether or not for this winning function right here. So what I'm going to do is I'm going to say I want to assert that winning p, when I call it with the array of bools where it is true, 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 and then false, 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 false. So this right here is just a specific example. And when I call that, that should be equal to true. So that right there is a little unit test. So if I write this unit test and I go compile my program, then it's not going to say that there's 799 theorems. It's going to say that there are 803 theorems, because I just added a new theorem. So the normal development processes that you use with normal programs, you just apply those to reach. You write unit tests, except that those unit tests you can write as assertions. And in fact, it's even more powerful than that, because notice that this really only checks whether these are false, but actually this thing should return true no matter what these are. So we can actually do that. We can express that, because we can write for all booleans in this spot, and we can write for all booleans in this spot right here. And so this is something that isn't really available in normal programming, but is available inside of reach. Let me go compile again. And so this for all basically says create a meta variable that will just be filled in, and it will explore all the possibilities. So it'll say, does this thing result in true if this is true, if this is true, if that's false, if this is false, and so on. So when you write unit tests in reach, you're writing something much, much more powerful. So I guess what I'm saying is that the question on debugging is use standard tools and use even more powerful reach tools that reach makes available. That was a long answer to the first question. Hopefully every question will have an equally long answer.
Hey, AJ, I'm going to actually answer a question or ask you questions that I see up here. So how might a program with role switching work? For example, someone takes over a contract.
When we write this program right here, every time, so when the program starts, there are these identities, Alice and Bob. But like when we run the program, we don't really know beforehand that Alice is Jay and that, Bob is Chris. So when do they really get set to be a particular person? Basically, the idea is that the first time that Alice publishes, she takes on the role of Alice. And the first time that, let me say it like this. The first time that Jay publishes as Alice, he takes on the role of Alice. And the first time that Chris publishes as Bob, he takes on the role of Bob. And so now in the future, when this right here, when this Alice publish happens, that's going to check to make sure that this message really actually came from Jay. Okay, so now how do we make it so that in the future, there's some other way for someone else to take it over? There's sort of two ways to think about this. One way to think about it is to imagine that there's a third participant that we'll call C, and this will be Claire. And actually, let's just say that Claire is just another Alice. So we got C right here. And then what we would do is we would have some message that Alice could send it. I'm kind of like randomly typing stuff, so I'm not going to be able to fully flesh this out. But essentially what we would do is we would say that A would publish Claire's address. And then after she published it, we would say C is set to Claire's address. And then we would basically have some state about whether to expect messages from A or C. And so the thing is that role switching is a concept that you have in your interaction between these participants, and you would explicitly write that down. There's no global thing where you can just modify and say A is going to become this other person. That's actually kind of an interesting idea. I think it might be possible to implement something like A becomes Claire address, but that feature isn't supported. But what you would do is that you would explicitly encode in your program the option of one role taking over for another role.
Thank you, Jay. Another question is, it's about actually storing data. First, if you could just quickly, go over how the commit reveal works with Alice and Bob Hand to make sure that Bob doesn't know what Alice did.
So all that code is right here. What Alice is going to do is she's going to pick a random number. And if she published this random number, then Bob would be able to look at it and do something like this to make sure that he won. So she doesn't want to just share it. Instead, what she does is she digests it. That means that she cryptographically hashes it. And she shares that cryptographic hash. And then what Bob does is he just publishes his random number straight. And then what Alice does is she now reveals the number that she chose earlier. And then we verify that the thing that she committed to is equal to the thing that was actually provided. And this is called the commit reveal pattern. It's an extremely common pattern that exists in blockchain programs. Now that was step one. Now that was step two.
Yeah, I think the commit reveal actually exists in most of our example applications.
Yeah, it's really common.
The second question is a little bit more in depth, and the question really is with a feature that's not released yet. It's the linear state, or what we call containers. How are we going to be able to actually store that data on Algorand?
You're sort of like alluding to something that's off screen. So let me answer the question that you're asking off screen.
Thank you.
In this program, you could ask yourself, what is the state of this program? And remember that for many people who write blockchain programs, especially when they write in tools like Solidity, basically step one is you say, what is the state of my program? And then after you think about what the state is, you then start thinking about what manipulations of state are possible. And as you can see, Reach doesn't work that way. Instead, when you write a Reach program, you think about who is playing the game and what do they do at each step. But of course, when it ultimately gets compiled, what really happens is that we have to go figure out what the state is. So how does that happen? Here's an intuitive way that you can think about it as a Reach programmer. Right here, we publish wager amount and commit A. And down here, we look at commit A. And in between, when we published it and when we look at it, there was a commit right here and a commit right there. And those two commitments, they basically mean that the consensus program is over. So publishes are kind of like arguments to like the protocol event handler, and commitments are kind of like the return from that. So given that we look at commit after it's been, we look at commit A after it's been committed, and it's not one of the arguments, that means that it must occur and it must be contained inside of the state. So intuitively, the state of your program are whatever variables are looked at in the tail of the program. You can pick any line of the program. All the variables that are actually looked at down below that line, they are in the state. This program, the compiler does all sorts of exciting things to try to reduce that state. And one of the things that it does is it's going to compress the entire state of your program down to just a hash of all of the free variables in the program. Okay, so now, in the future, what if you want something like an NFT or something like that, where you have a mapping from users of your program to information? Like, let's think about something like an auction system, where every user we're going to store what is going to be bidded. So the way that looks in your Reach program is you're going to create a container, and that container is going to be a mapping from identities to a number. And now how are we going to compile it? Okay, well, there's not really a short answer to this. Well, there's a short answer, but it requires you to know a lot about how Algorand works. But basically, stateful contracts, they don't just have their own global state. They also have what's called local state. And this local state is essentially a built-in mapping in the protocol from every account to some information keyed on the particular address, in the particular application. So basically, the way that the Reach compiler works is you say, I need this mapping. And what that really means is that every user of your program is going to opt in, buy some space in that mapping, and then give access to the application to store things there. And so rather than there being applications like on Ethereum, for instance, where the application has a hash table, instead the way that you kind of think about it is that every user has a hash table that they just own on Algorand. And what they can do is they can give access to slot from that hash table to particular applications. And the way that the reach compiler works is that it automatically manages that for you. Now, when I say automatic, it's from the end user's perspective, they see it happening. Because like if we were using like AlgoSigner and we ran this tic-tac-toe program, every single step of the program, you're going to sign a bunch of transactions. You're going to sign, I think, 5 transactions. And if we were using this container system that I've just talked about, rather than signing 5 transactions, you would really sign 6 transactions, because one of them would be opting in to allowing the application to have to use your storage. And so that would be observable to the end user, but you as the developer, you don't have to worry about that.
Wonderful. Well, Jay and Chris, I wanted to thank you guys both for joining us here in the developer office hours here. Learning about Reach was really exciting, very in-depth conversation. Thanks again, guys, for joining and answering all the questions.
Absolutely.
Once again, we'll be having
more stuff. You can join our Discord server and talk directly to Reach developers. Also, we are on the Algorand Discord and we're on the Algorand Slack if you are already talking there and want to have Reach conversations in those communities.
That's great. So that's again docs.reach.sh. Thanks again, guys, and have a good rest of your day.